Okay, good morning, everybody. Welcome to an overview of standard ranges. My name is Tristan. Hope everybody's in the right place. First question, show of hands. Who's on Twitter? A lot of you. Who follows Bryce Lellback on Twitter? Well, more of you should. So last week, or perhaps it was the week before, Bryce tweeted this. He tweeted CppCon bingo. And your CppCon bingo card looks like this. And right off the bat, this is the very first session, well, other than the keynote, I've given you a box to tick off because this is indeed a hipster reveal.js presentation. So there you go. Just for coming to this presentation, even if you get nothing else out of it, you can tick off one of your CppCon bingo boxes. In fact, by the end of this talk, you should be able to tick off an awful lot more. So, you know, if you're playing bingo, you've absolutely come to the right talk. Okay, so who am I? Well, as I said, my name is Tristan. I'm an independent contractor, freelancer based in London in the UK. I'm a member of the BSI, that's the UK C++ national body for standardization. I'm also the director of an organization called C London Uni. You might have heard us talking on CppCast or CppChat. We're a non-profit, we offer free beginner C++ classes in London and also online. So if that's something you're interested in talking to me about, then please come and find me afterwards because I'm very happy to talk about it. Anyway, onwards, today's talk. So today, I'm hoping that by the end of the session, by the time you leave this room, I'll have been able to answer 3 questions for you. First of all, what is this ranges stuff all about? You're here, I guess, because you've heard that we're getting this new, fancy, great new stuff in C++20, and you want to know what's it all about. And in particular, what's in it for me, by which I mean you. And thirdly, how can I use this stuff today? Yes, it's coming in 20, but there are 3 implementations that I know of this stuff that you can use today. And so I'm briefly going to go over at the end what those implementations are and how you can get them and how you can use them. So actually, just on this, using the stuff today, how many people use Range v3 in production or for personal projects? Actually, a lot fewer of you than I expected. Who has heard of Range v3 but hasn't really tried it out? Okay, so majority of hands. And lastly, who uses STL algorithms in their code today? Okay, I'm hoping that's every hand in the room, right? Because it really should be. So if you're in that last group that put your hand up, if you're not, shame on you. But if you're in that last group that put your hand up, then this is a talk you should be interested in. Because the standard algorithms that we know and love today are going to get even better. And that's mostly what I'm going to be talking about. So let's kick off with question 1. What is this ranges stuff all about? Well, if you really had to boil it down to, a really simple, pithy, one-line phrase, just 6 words, STL 2.0. Right, so very, very brief history lesson. 1994, Alex Stepanov and Meng Li, they produced their masterwork, their magnum opus, the HP standard template library. 1998, large parts of this become part of the C++ standard library. And then we fast forward a bit, and not really much has changed. We've got a few new algorithms in C++11, a couple of new overloads in 14 and 17, but by and large, what we have in the standard today is more or less what Stepanov and Li came up with 25 years ago. Now, you could argue, and I probably would, that this actually proves that this was a good design that has stood the test of time. But C++, the language, has evolved considerably in that time. We can do things today that we simply could not do in 1998, let alone 1994. So it's time to take this venerable library that we've been using for a quarter of a century and to update it for today's C++. And as I say, if you really had to boil it down to what this ranges stuff is about, it's STL 2.0. It's a new major release of this piece of software. And like any new major release, we're getting lots of new features. And most of the talk today is going to be about these new features. In full disclosure, because it's a new major release, new 2.0, it's not quite 100% backwards compatible. It's more permissive in some ways, more strict in other ways. So if you're one of these places that uses lots of custom iterators, custom containers, there's a possibility you might need to change slightly some of your iterator definitions in particular. But that's a rare sort of corner case. And 95, 98% of the time, you're going to be able to jump straight to ranges and reap the benefits without having to do anything except change the namespace. So all of the new facilities that we're getting are going in this nested namespace std ranges. And your old code that uses namespace standard will continue working just as it always has. So all the new stuff I'm going to be talking about is not going to break any code. This is opt-in. You opt in to the new stuff in this standard namespace, standard ranges namespace. So just as an aside, I don't know if people have been following this for a while, there was a proposal that we should have a new top-level namespace, which is std2. And this was actually reserved in C++17. We've reserved std followed by any number of digits. In the end, it was decided that a nested namespace within std was probably the way to go. I think people were kind of worried about like a Python 2.3 situation, like bifurcation kind of thing. So we're getting this nested namespace instead. Everything that I'm going to show you today, all being well, barring an absolute disaster, will be part of C++ 20. That's another box you can tick off on your bingo. Promising something is going to be in the standard version. No, everything I'm going to show you today is in the C++ 20 committee draft. That's the stage we're at, is standardization. And at the moment, it's just a matter of sort of dotting the I's, crossing the T's, making sure everything's right. So everything I show you today should be in C++ 20. And as I mentioned, there are 3 implementations, 3 libraries that are compatible with older versions of C++ that you can use today if you want to get a head start and start using this great new stuff in your code. So far I've said the word ranges probably about 200 times. Perhaps we ought to take a step back and say, well, what is a range anyway? Well, a range is an object on which you can call begin, where begin returns you something called an iterator, which can be incremented, which we can dereference to obtain the value at that position, but which we can increment until it compares equal to the thing we got from end. Like, for example, a standard vector. So if this seems familiar, it's because it's more or less the same definition of a range that we have today. Ranges don't replace the use of iterators. They build on them. So I spend more time than is healthy on Reddit, on the CPP Reddit, right? And I see comments on there from time to time of people going, oh, well, iterators are the old stuff. Iterators are old, and now we're going to have ranges, and if you use iterators, you're wrong. That's not the case. Yes, we've got these new abstractions on top of iterators, but iterators are still there under the surface doing the work, just like they always have. This is evolution, not revolution. Yes? Does end have to return an iterator? In about half an hour, you'll get the answer to that question. So the ranges work formalizes many of the notions that were implicit in the existing STL. We already had this notion of a range, like a sequence of values that we can iterate over. We have range-based for loops. We've had these things for a while. And ranges really formalizes a lot of this language. So that's sort of the 1,000-mile view, the really high-level view, where is this coming from? Why are we doing it? But the really important thing, the thing you all want to know, the reasons you're here, unless you heard an English accent and thought it was Matt Godbolt, in which case, sorry. What you really want to know is what's in it for me. Why is this a good thing? How is this going to make my code better? And so the bulk of the rest of this talk is going to be about answering this question. So the first thing we want to talk about is concepts. Now, talking about concepts would easily be an hour-long talk just by itself. And there are, in fact, talks this week that will go into a lot more detail about concepts than I can do when I have a lot of other things to talk about. But as many of you probably know, concepts are a new language feature that we're getting in C++ 20. They had a sort of long and tortured history. They were originally part of C++ OX, which became C++ 11. They were sort of yanked out at the last minute, reworked into this new sort of simpler form called Concepts Lite. Concepts Lite eventually became the Concepts TS, and then the Concepts TS, again, underwent some modifications and is now going to be part of the next standard C++ 20. So the concepts language feature has been available in GTC for a long time. You use the fconcept switch. And in fact, just a few days ago, last week, Microsoft announced that the new version of MSVC, the new preview version, is actually going to support concepts, which you have to give Microsoft a lot of credit because they have done absolutely stunning work in updating their compiler to the latest standards. So kudos to them. There's a Clang implementation in progress. As far as I know, unless anyone can correct me, it's not part of not part of Trunk yet, but it is there on Compiler Explorer, and you can play with it. So all three major implementations are working on this, and so fingers crossed in a year or two, we'll have concept support in all of our compilers. So what do concepts actually do? Well, concepts allow us to control the instantiation of templates by testing syntactic conditions. And again, if you really wanted to boil this down to a pithy phrase, and I'm aware that I'm on video and I probably shouldn't be saying this on video because it's something that people who are really into concepts won't like me saying, right? But if you needed to explain it to your coworkers in 3 words, it's Svine on steroids. Or perhaps Svine in the language. So for years, we've been able to do these horrible hacks using standard enable if. Later, we got void t. We have these methods of constraining our templates today, but they're horrible, let's be honest. They're sort of abusing these template instantiation rules. They were kind of, as far as I know, discovered by accident rather than designed into the language. So concepts give us a much nicer way of doing this, a much better way of doing this that is part of the language and hopefully usable by mere mortals as opposed to template experts, because who wants to be a template expert, really? So a concept is a compile time predicate, that's a true or false value, which is true if the given type meets requirements we give it. So we can say for a type T, given an instance of that type, will some expression compile, and is the type of that expression, does that meet certain other criteria? So here's an example of a concept. It's not a very good concept. I have to say, don't use things like this in your own code, but it's one line and it fits on a slide. So here we've got a concept called string convertible, and what we say is that we require that given a const reference to a T, we are able to call the member function t.toString, and this returns something that is convertible to a standard string. Okay, so as I say, this is not really a great example of a concept, but just sort of demonstrating the syntax more than anything. So how can we use these? Well, as I say, we can use these to control the instantiation of our function templates and class templates. And we do that like so. So here we've got a function template, convert to string. And in the body of this, we call t.toString. But we've used the keyword requires to constrain this template so that it's only usable by types which meet the requirements of the string convertible concept. So if we try and instantiate this template with a type that doesn't have a toString method, this function template is going to disappear from consideration for overload resolution. And if it was the only candidate, we'll probably get an error message saying, well, I couldn't use this because key does not meet the requirements of string convertible. As I say, this is like the 3-minute version of concepts. And I do encourage you, if you don't know a lot about this, to go to some of the other concepts talks this week, if you want to learn more. This is the sort of long-winded way of writing these things. In some cases, we can use a shorthand version. We can write things like this. So this is exactly equivalent to what we had before. This says convert to string is, again, a function template. And now we require that T matches the string convertible template. We can actually abbreviate this even more. This was something that was controversial, that was a lot of people didn't like, and there were a lot of arguments about in the standard committee. But eventually we reached a consensus that you would also be able to write it like this. There's actually a slight typo on my slide, apologies. That should be constant auto-ref. But the meaning is clear, or should be, or is hopefully, that this is saying that this is some deduced type, and the deduced type must meet the requirements of string convertible. So this is still a function template, even though we're not using the template keyword, but rather like with lambdas, the appearance of auto in the parameter list specifies that this is actually a template. So again, really had to rush through concepts. So you're all concepts experts now, I hope. Well, maybe not. But you know perhaps what they are at least. So that's a language feature. But actually what the ranges work gives us is we're getting lots of new low-level concepts defined in the standard library. Things like standard same as, standard constructible from, standard convertible to. These are new low-level concepts that we can use as building blocks for defining our own concepts. So these largely replace all the things that we have in the type traits header today. We can use real language concepts, and we can use those to build up our own concepts that we can use in our own code. On top of that, the standard library C++20 builds its own higher level concepts, as we should be doing in our own code, so the standard library does. And it introduces these higher level concepts, things like bidirectional iterator, things like random access range. And these are built out of these lower level concepts. So we've got these concepts that we can use to constrain our algorithms, and in fact, to constrain our functions, and in fact, that's exactly what the standard library will do with all the algorithms that we already know and love from the STL. We'll be getting constrained algorithms. So why is that a good thing? Well, let's have a little example. Who's seen code like this before? A few hands, not many people want to admit, right? Because nobody writes this. Because, well, is this going to work? No. Why is this not going to work? I hear an Australian voice in the front row. Sort requires random access iteration. Yes. And a list iterator is only a bidirectional iterator, which you all knew, of course. Everybody said this wasn't going to work, because you all knew that standard sort requires a random access iterator, or a pair of random access iterators. But the compiler doesn't know that. So what's going to happen when I try and compile this code? What's going to happen when I try and compile this code? Template error messages, yes. Last time I gave this talk, there was a shout from the back of kaboom. Yeah, we get something that looks like this. yeah, and like this. Oh, yeah, and like this. Oh, yeah, and like this. And I'm not sure if this is going to work, but this. Right, and by the way, I haven't made this deliberately bad just for the purposes of demonstration. I did this today with the latest Apple Clang on my laptop. This is actually what happens. 442 lines of error messages for a 2-line program, right? You want to know the reasons that people complain about C++, the reasons people don't like using C++. One of them that will rank pretty high on the list is this template error spew. If you get something wrong, if you're a newcomer to C++, it's not necessarily obvious why you can't sort a linked list. And then when you try and do it, you're confronted with this, 442 lines of errors. I mean, where do you even begin? So let's try again. This time, instead of standard sort, we're going to call ranges sort. And again, no tricks, nothing up my sleeve. I did this morning with my ranges implementation that I'll tell you about later. This is the entire error output. That's it. And if we scroll over here, you'll see that we see candidate template ignored, requirement random access iterator of a list iterator was not satisfied. And the second message is saying that the second candidate was ignored because a list iterator is not a range, which I'll get onto in a second. So we've gone from 400 plus lines of error messages to, 8 or 10 lines that make it exactly clear what the problem is. So, there's a lot of other ranges stuff I'm going to tell you about for the next 40 minutes or so. But just for me personally, if the ranges work brought us nothing else except this, except better error messages, for me that would be worth the price of admission alone. I think this is fantastic and is going to make such a big difference to the everyday experience of people using C++. I really think this is great. So the second thing that is going to, it's not world-changing, but it's going to just make your everyday experience of using the standard library that bit nicer. We're getting range-based overloads. So here we have almost identical code to what we had before, except this time we're using a standard vector. So this is going to work. This is fine, this is good code, this is what you write today. In fact, this is what you write a lot. Dot begin, dot end, dot begin, dot end, dot begin, dot end. You probably write it, if you're anything like me, you write it dozens of times a day. Right? No more. With the new ranges libraries, we're getting range-based overloads. You will finally be able to say standard ranges sort of my vector, of my range, whatever that range might be, and it will sort the whole container for you, the whole range for you. At last. One slight note of sadness, one slight confession. I'm sorry. As it stands in C++20, it's only the algorithms that are in the algorithm header that are getting this rangification treatment. There are other algorithms in the numeric header that won't be updated yet. Fingers crossed for C++23. But the vast majority of algorithms that appear in the algorithm header, you'll be able to use. Range-based overloads, you'll have constrained calls, better error messages. Life will be better. You have what you had before, but better. And that's what a new major release is all about. So those two features are really about taking what we had before and making it better. But we're also getting some new things that we didn't have before. Things that are strict improvements. And one of those, sort of subtle, but it's about Sentinels. So I gave a sort of very hand-wavy description of what a range is, at the beginning of the talk. I said the range is something upon which you can call begin and end, where begin returns you this thing called an iterator, and we can increment the iterator until it compares equal to the thing we got from end. And I was very astutely pulled up on this at the front, because this was a deliberately hand-wavy thing, because in the new ranges world, begin and end don't necessarily need to return the same type. In the existing STL, end must return an iterator. Begin and end must return the same type. But as I say, in the ranges world, we have this new idea of a sentinel. And a sentinel's only job is to mark the end of a range. Oh, I'm sorry. There we are. So a sentinel is some type that is equality comparable with. That's one of these new low-level concepts I was talking about. Sentinel is some type that's equality comparable with its corresponding iterator, which denotes the end of the range. So why do we want these things? Well, the first thing is that if you're using your own custom iterators, using separate sentinel types in some cases allows us to simplify writing our own iterators. And, you know, that's nice, but not many people write their own iterators. What I like even better about Sentinels is that in some cases, they actually allow us better code generation. That is, they give the optimizer more information upon which to optimize your code, and so you get faster code. And who doesn't like faster code? So let's show you what I mean. Here we've got an imaginary function called readFile, whatever our custom file format is. This reads in a string. Big string, several megabytes maybe. And we know, because we wrote the readFile function, we know that this string is guaranteed to contain a new line character. Perhaps it's because readFile just pops one on the end when it loads it in. Okay, we know for a fact that big string contains /n somewhere. But it might contain more than one. So what we want to do is we want to find the first new line character that appears in our big string that we've read in from the file. So we begin at the beginning. We compare every character to see whether we've got a /n. It's a linear search. Linear search, of course, you use standard find. Getting into Sean parent mode, right? Obviously, that's a find. So this is how you do it today. We search from the beginning of the string to the end of the string for the /n character. And this is fine. This is good. There's nothing wrong with this code, right? This is good code. We'll pass code review today, I hope, in your organizations. But this is not optimal. And the reason it's not optimal is because we have extra information that we're not communicating to the compiler. And really, to get a sense of that, let's have a quick look at an implementation of standard find. So this is a conforming implementation of find as it exists today. We take two iterators. We say, while first is not equal to last, that is, if we're not at the end of the range, we compare the value at the first position to the given value. And if that matches, we break out of the loop and we return the iterator that we're currently pointing to. If not, we increment the iterator and we start again. We say, are we at the end of the range yet? Okay, no, we're not. Let's test to see whether we've reached the value. The thing is, we know, because we wrote our readFile function, we know that we're going to find a new line before we reach the end of the range. We're sure about that. We are 100% sure. So this first condition, while first not equal to last, that is never going to return true. We are always going to break out of the loop before we reach the end of the range. But the compiler doesn't know that. We've got no way of communicating it in today's world to the compiler. Well, in the ranges world, C++20 world, we have. We have this new special Sentinel type that's called unreachable Sentinel. And what an unreachable Sentinel is a sort of, how to put it, a Sentinel that you can use with any iterator type that always returns false when you say, is it equal to an iterator? For any given iterator, unreachable Sentinel will return false from its overloaded operator equals equals. That is to say, with this version of ranges find, we are communicating to the compiler now that we can never reach the end of the range. So our sort of pseudocode implementation or specialization of find looks something like this. I didn't want to put in all the string iterator noise, so we'll stick with I and val for now. But now we have our unreachable Sentinel for the last. And now the compiler is going to compile this code, and it's going to look at this condition, while first is not equal to last. Well, an unreachable Sentinel unconditionally returns false from operator equals and returns true from operator not equals. Unconditionally. And this is all, inline functions. The compiler can see this. The compiler can use this information. The compiler effectively transforms this into while true. It removes a comparison. We were previously doing 2 comparisons for every element in the loop. We are now doing only 1. So I have a link there to Compiler Explorer that I was going to show you, but I'm not 100% convinced I'm going to be able to flick back to the slides. So you're going to have to take it on trust that this actually does compile to shorter assembly. If you want to look at the slides later, you can go to this link yourself. You can verify it for yourself. But just for now, you're going to have to believe me that this actually really does make a difference. And you can benchmark this and show that it makes a difference in actual micro benchmarks as well. This is good stuff. This is making your code faster. And yeah, who doesn't like faster code? Okay. Talked about constraint calls, range-based overloads, this new feature we're getting called Sentinels, which is perhaps not something you'll be using every day, but something that you can use that is there, a new tool in your toolbox when it's appropriate. Let's talk about something else that actually, in my experience, not a lot of people know about. And that's something called projections. So a few of you, perhaps a dozen of you, put your hands up at the beginning when I asked who uses Range v3. So who are those people again? Eric Niebler at the back put his hand up. I wonder why. So of those people who put their hand up, who uses projections? Chris does, yeah. So my experience with this is that even for people who are using ranges, who are using using Range v3, using one of the implementations, projections are sort of a bit mysterious and a bit new and a bit weird, and people aren't really familiar with them. So my goal over the next 5 minutes or so is to try and demystify what projections are and show you an example of how projections can, make your code look prettier. So demystifying projections. Well, what is a projection? Okay, a projection is a unary callable which may be passed to most algorithms and which modify the view of the data that the algorithm sees. Okay, that's nice and clear, right? Move on. No, I'm not sure that this demystifies it very much. Let's try and have a look at an example to see if that can demonstrate what I'm talking about a bit better. So here we've got 2 structs. We've got an employee and a payslip. So an employee has a name and an ID number, and a payslip has the pay info. We don't really care what that is. The employee might, but we don't really for the purposes of this demonstration. And a payslip also has the employee ID, the employee to which the payslip corresponds. And we've got a vector of employees, and we've got a vector of payslips. Perhaps we're writing, some accounting software or whatever. We have a vector of employees and a vector of payslips. And our job, what we want to do, our goal is to make sure that every employee receives exactly one payslip every month. Okay? We don't want an employee to receive 0 payslips. They wouldn't be very happy about that. We don't want to pay any employee twice. The company wouldn't be very happy about that, although the employee would probably like it. So we want to make sure every employee has precisely one payslip. So can anybody think of how we might do that, given these definitions that are on the screen right now? No volunteers. Okay. Well, one way that we might do it is we might think, okay, how about I sort my vector of employees according to their ID, and we sort our vector of payslips according to the employee ID, and then we compare those two vectors by their respective ID values and make sure that they contain the same IDs in the same orders. Right? Sorry? Intersection. We could, but, I've written sort on the slide, so that's what you're getting. So this is what that approach might look like today with the existing STL. We can say, we sort our employees, we pass a custom comparator that compares their IDs. We sort the payslips vector, again with a custom comparator comparing the employee ID field. And then finally, we call this standard equal algorithm that makes sure the two vectors have the same elements in the same order. And again, we pass a custom comparator to that. Well, of course, I've just explained we're getting nice new range-based overloads. So the first thing we want to do is make use of that. Get rid of all that begin and end noise. So things get nicer already. But we can make this better still. So remember what I said at the beginning, or the beginning of this section. Projection is a unary callable that we can pass to most algorithms, including the 3 that were on the screen just now. And a projection modifies the view of the data that the algorithm sees. So let's narrow it down. We'll just look at our first call to sort. So we're sorting the employees vector using this custom comparator. And the custom comparator says, okay, if X's ID field is less than Y's ID field, then I'm going to use that information to sort the vector. Well, we can modify this to use a projection to project each employee to its ID field. So we've added an extra parameter this time. This time we're not using a custom comparator. We're using one of the standard comparators. Standard range is less. This is more or less the same as standard less that we've got at the moment, except uses the new concepts, constraints. So we've got standard range is less. And now we're passing a new parameter, which is the projection. So we are projecting each employee E to its ID field. So now sort is operating, as far as sort is concerned, it only sees integers. Sort is operating purely on ints because each employee has been projected to an int. And we can apply this to our other call to sort and to equal as well. So now we're using projections for our 2 sort calls. And for the call to equal, we're using the equal to comparator, and then we're projecting the employee and the payslip to their respective fields. And you might look at this and say, well, that doesn't actually look like too much of a benefit to me, right? Because, well, it's still using lambdas, still using a lot of noise. But in fact, the way projections work, the way this is specified in the new standard, is that these projections are going to be routed through an implementation of standard invoke. And standard invoke, for those who don't know, has a bit of magic. has a bit of magic that lets you treat pointers to members effectively as callables. So we can use this new magic that's in standard invoke to replace these lambdas with pointers to member data. So we can read this and say, okay, we're going to sort employees using the less comparator where each employee is projected to its ID field. And we're going to compare the employees and payslips vectors using the equal to comparator where each employee is projected to its ID field and where each payslip is projected to its employee ID field. We can actually make this better yet, because the default comparator for sort is to use less. The default comparator for equal is to use equal to. So we can, in fact, just default construct these parameters just by using an empty pair of curly braces. So we now say we want to sort employees using the default comparator where each according to the employee ID. We want to sort the payslips using the default comparator according to the employee ID. Then we want to compare employees and payslips using the default comparator according to the employee ID field and the payslip employee ID field. So this was our original standard, today's C++ 17 standard code. And this is what we're getting in C++ 20. This is what you can do with the new functionality. Yes? Well, then you might have to use a different approach. You know, this is, yeah, there are various ways of doing this. Well, if you want to sort, you have to, you know, take a copy then, I guess, or, yeah. We use a different approach that doesn't involve sorting. You didn't know that. Wow. By the way, do you know how nerve-wracking it is for me talking about ranges when Eric Niebler has a question in the back row? Of course, yeah. Yeah, so Eric makes a very good point, is that I was slightly lax in my terminology on the slides. I'll remember that for next time. But actually, this is going to sort the employee struct themselves, right? This is not just going to swap the IDs, because that's definitely not something you want to do. Although, perhaps if you got your ID swapped with the manager's and you got his payslip, you wouldn't complain. Same amount of money as the company's concerned. Anyway, yes, so this, as Eric, of course, rightly points out, this is going to swap the employee structs. Yes?
So actually, I was going to ask a question that Eric half answered, and the other half of that question is, then each algorithm then has to say what it does with this projection. It's not a general rule that the projection of the others apply where everything's down and stuff. The algorithm has to stop what it does with the projection.
Right, and so the algorithms, you're saying the algorithms have to document what they do with the projections. And in fact, they do exactly that. So if you read the standardies, and on CPP reference as well, I'm sure, it actually documents how many times these projection functions get called for all of the algorithms. Yeah. And actually, it's not your question, but just came to mind while you're saying it. There are actually default projections that is just like a pass-through. That is what so these are like default parameters, and the default parameter is just a pass-through projection that the identity projection the compiler can see straight through. Yes? Yeah. So we're using here we're using a pointer to a member data as our projection. What if we wanted to use a getter function? Say we can use a pointer to a member function as well. That works just fine, yes. Yeah. Yeah. One more and then we're going to have to move on.
So are the projections type-based in the sense that if I switch the ID and the employee ID, they happen to be the same type in this case, but what would happen if I swapped the position of those two projections?
So if you were to switch employee ID, employee ID and payslip employee ID in this function call, it would not compile. Oh dear. This is not good. There we are. So it would not compile because it's using a pointer to a member and it's just the wrong type for the pointers. Okay, so the last thing I'm going to talk about today, before we get on to the implementations, is perhaps the biggest headline feature, and perhaps the one that you are most interested in. So I want to talk about views. So I say, where are we? We've got about 15 minutes left. So I can't do justice to what views can bring to your code in 15 minutes. In fact, you could do an entire talk or a couple of hour talks just on views and range adapters. And the good news is that this week people are doing exactly that. There are many talks about ranges this week. And whilst I'm giving kind of the broad brush overview of what the new features are, there are people who are going into more detail. So I really encourage you, I'm going to give you the very short version, but I really encourage you, if you are interested, to have a look through the schedule, look at the ranges talks, and pick out the ones you like. So, views, range adapters. Let's begin at the beginning. The standard algorithms are great. Everyone agrees, right? Standard algorithms are great. Standard algorithms are great, and they're going to get even better. Everything I've talked about so far is about making the standard algorithms even better. But the standard algorithms have a drawback. And the drawback is they don't compose well. And what I mean by that is they perform their operations eagerly. So again, a very short code example to show you what I'm getting at. So here we've got a function called print squares. Very simple. All we do is we iterate over every element in the vector, and we print out the square of that int, right? Pretty straightforward, hopefully. But we are very diligent C++ programmers. We watch a lot of conference talks. We attend a lot of conferences. We listen to the experts. We listen to the masters. And in particular, we listen to Sean Parent. And Sean Parent says, no raw loops, right? Prefer the standard library algorithms whenever it's appropriate. Now, in fairness, of course, Sean was not talking about, trivial one-line for loops like this. No, definitely not. But I didn't have space on the slide to fit a whole implementation of rotate on there. So you got a very simple one. So although this is simply a demonstration, let's take the spirit of what Sean means and apply this to our little print squares function. So there are a few ways you could do this. Here is one. We're going to use standard transform, which is going to become ranges transform. And we're going to transform our vector. And we're going to place the output from this calculation into this OStream iterator. This is the same OStream iterator we already have. So if you're not familiar with it, you can look this up. This is not changing. So we're going to, again, iterate over our vector, call this function, perform this calculation for every element in the vector, and then we're going to print the output. So this is equivalent to what we had before. This is taking the spirit of Sean's advice, albeit in a situation that you shouldn't actually, because we did just have a trivial loop, but taking the spirit and using a standard library call instead. But what happens if the requirements of our function now change? So instead of print squares, we want to print the even squares. So back to our for loop implementation. This, again, is pretty simple. We iterate over every element I in the vector. We say, if I modulo 2 is 0, that's if I is even, we're going to print it. And otherwise, we just skip to the next element. Fairly straightforward. But how do we do this using the standard library algorithms? This is not so easy. Okay, well, here's one way you might do it. There are, again, a few different ways that you could approach this. This is one way that you might do it. You might say, okay, well, we're going to remove all of the odd elements. And of course, the remove algorithm actually reorders the container, moves all the false elements to the end. So we're going to reorder our container, move all the false elements to the end, and then we're just going to, again, as we did before, transform the subset of these elements that are true. And this is fine, this works. But it's not great. We're having to modify the vector when we didn't before. You see, we're now taking the vector, we're taking a copy of the vector, whereas before we were taking a const reference. And the reason we've had to do this is because the standard library algorithms operate eagerly. That is, we've had to remove if has had to finish all of its work before we move on to doing the transform. So C++20 includes new range adapters, these things, mysterious things we call views, that offer lazy evaluation. This is something functional programmers have been doing for years and something that we will be getting in C++20. So what does this look like if we use these range adapters? Well, it might look something like this. So here we're making use of two of these adapters, namely filter and transform. So let's look at the inner filter call first. So we're saying we want to adapt our vector, adapt this range, and we want to filter so it only returns those elements that are true. So ranges views filter that you see there returns a new range, but a lazy range. It does nothing until you start to iterate over it. It's an adapted range. And then we pass this adapted range into a second adapter, into a transform adapter. And this transform applies this square function every time we dereference one of its iterators. So we set up this view, these nested adapters, we filter, and then we transform. And then, finally, we copy the values into the O stream as we did before. So it's worth pointing out that actually no work, no iteration happens in the setup step, in the view step. That just sets up the transform and the filter that we want to do. The work, in this case, the actual iteration, happens in the algorithm call, in the copy call. The rest is just setting up our adapter schemes, our adapter scheme. And this, this is great. This means that we can now just have our const vector again, and we're going to lazily apply this filter and this transform as we iterate only once over our vector. And this is good. But, we can make it even better. And the problem with this is that it's sort of inside out. Because first of all, we're filtering the vector, and then we're applying a transform. And so you have to read this sort of inside out. And the equivalent functionality in other languages, you'll know, C#, for example, you can just do, dot this, dot that. You can set up your calls so they form a linear sequence. And the ranges work has overloads that allow us to do this. So this is exactly equivalent to what we had before. Oh, except I've got the two, I've got the two lambda calls the wrong way around. Apologies for that. But imagine that I have not made that mistake. So this is, we've got an overload of the bitwise OR operator. And you can think of this sort of roughly, not exactly, but roughly like the pipe operator in Unix. So we're taking our vector and we are piping it through the filter adapter. And then we are piping the result of that through the transform adapter. And now the flow of data is clear. It flows from vec, through filter, through transform. And then we're applying this copy. So I am a little bit pushed for time, so I can't tell you as much of this about this next one as I wanted to. But we can actually make some quite complicated pipelines. So this is from a library I wrote a couple of years ago. It uses range v3 to translate between different Unicode encodings. So we read in a file, we consume the Unicode byte order mark, we convert internally to UTF-16, we prepend a byte order mark to the front, convert it to big endian, and then apply a view that makes it appear as if these are bytes. And then we can copy to an output file. So this copies from UTF-8 to big endian UTF-16 using this sequence of transformations. So this does it without ever loading the entire file into memory. This does it on the fly. And unfortunately, running short on time, so I can't quite go into it as much as I'd like. But if you are curious, the URL is there on the screen, and I'm happy to talk about it afterwards. But just in the last couple of minutes that we have left, let's quickly go over the third question that I asked right at the beginning, which was, how can I use this stuff today? So there are 3 implementations that I know of that are available. They're all open source. They're all on GitHub. You can use them today. So the first one is range v3. Primary author is that gentleman in the back row. This is Eric Niebler's original ranges implementation. This is the work from which everything else sprang. So it has everything that's going to be proposed in 20, and many, many extra views and actions, which we haven't talked about today. Extra views and actions, which are not part of C++ 20, and perhaps, hopefully, we'll see in 23. It's extremely popular, widely used, and even with my own internal bias, I have to say, if you are looking for a range implementation, if you want to use this stuff today, you can't go wrong with range v3. So C++ 14, I believe, works on all the major compilers, and it uses actually this kind of preprocessor magic to actually make use of core language concepts if they're available. If you are using a compiler, if you're using a new GCC that supports concepts, then actually range v3 can make use of that. Otherwise, it emulates concepts using all that horrible Sphene stuff we were talking about earlier. The second implementation is one you perhaps haven't heard of, called CMC-STL2. And this is the reference implementation of what was the ranges TS and is now C++ 20 ranges. This is the reference implementation by a gentleman called Casey Carter, who is the other big driving force behind ranges, along with Eric. So this uses language concepts exclusively. This is as I say, the reference implementation. So uses language concepts, so it's restricted to GCC or MSVC, possibly. I'm not sure, perhaps Chris knows the latest status, but I believe it does work. So CMC-STL2 now works with GCC and MSVC. No Clang yet, but I'm sure it's on the horizon. CMC-STL2 has a couple of extensions that are not part of the proposals, but by and large, it is what you are going to get in C++ 20. And just finally, very quickly, because I have to do it, because I'm standing here. This is one you almost certainly haven't heard of. It's called NanoRange, and this is my implementation of the ranges specifications. So this is an independent re-implementation from the specs that are published online. It uses C++ 17, works with Clang, with GCC, with MSVC. Doesn't use language concepts, but instead uses the lovely, clever template stuff to emulate concepts. Just the proposed features of C++ 20. There's nothing else in there. And the reason I've done this is because I want to provide a smooth upgrade path to standard ranges. I want you to be able to use NanoRange today and tomorrow to be able to upgrade to standard ranges, hopefully, if I've done it right, just by changing the namespace. Okay, I have used my allotted time and 30 seconds over, so if you've got questions, please do come and talk to me afterwards. I'm very sorry we haven't quite managed to have time for questions at the end, but thank you very much.